Hey guys. Before the first aircraft invented, flying in the sky is always the dream for human being. So people do everything possible to catch up with the missing wings, pursuing the fantasy to touch the sky. For many centuries, humans have tried to fly just like the birds. Wings made of feathers or lightweight wood have been attached to arms to test their ability to fly. The results were often disastrous, because the muscles of the human arms are not like a bird's, and cannot move with the strength of a bird. In 1480s, Leonardo da Vinci made the first real studies of flight. Mona Lisa was not his only masterpiece. He also had over 100 drawings that illustrated his theories on flight. The ornithopter flying machine was never actually created. It was a design that Leonardo da Vinci created to show how man could fly. The modern-day helicopter is based on this concept. Soon after, various forms of the flying devices come out. The brothers, Joseph Michael and Jacques-Étienne Montgolfier, were inventors of the first hot air balloon. They used the smoke from a fire to blow hot air into a silk bag. The silk bag was attached to a basket. The hot air rose and allowed the balloon to be lighter than air. It climbed to a height of about 6,000 feet and traveled more than 1 mile. But the first passengers in the colorful balloon were a sheep, rooster, and duck. People noticed that a good flying device has to be controllable, and that should make use of the wind. In 18th century, George Cayley, the father of the aeroplane, worked to discover a way that man could fly. He designed many different versions of gliders that used the movements of the body to control. He changed the shape of the wings so that the air would flow over the wings correctly. He designed a tail for the gliders to help with the stability. He tried a biplane design to add strength to the glider. He also recognized that there would be a need for power if the flight was to be in the air for a long time. That was a great milestone for the future aircraft design. A German engineer, Otto Lilienthal, studied aerodynamics and worked to design a glider that would fly. He was the first person to design a glider that could fly a person and was able to fly long distances. He wrote a book on aerodynamics that was published in 1889, and this text was used by the Wright brothers as the basis for the designs, who are the most well-known characters in history of aviation. They were pioneers credited with inventing the first successful airplane. The Wright brothers had gathered the aerodynamic data they needed to build a successful flying machine. Then the Wright brothers had built their latest glider based on this data. They had identified a wing shape that was efficient, producing the expected lift. And engineered controls that were responsive. The glider would also use a trailing rudder for yaw, therefore enabling the Wright brothers to navigate in the air in all 3 dimensions. Although the first flight of the Fly with engines lasted around 12 seconds and traveling 36 meters, the Wright brothers had made history with the first successful flight of a controllable self-propelled and heavier-than-air machine. That's the story of the evolution in early stage of aircraft history. Thanks to the efforts from all pioneers, we now can travel around the world, discover the beauty in different countries. Due to gravity, over hundreds of tons of steel floating in the air is a kind of miracle. How engineers make this impossible mission to nowadays airplanes. To make that becoming true, we should first get familiar with the magic that pushing the aircraft upwards. How planes actually fly. Because it has wings, but it's not made of feathers. The magic behind the wings is the lift force. So what is lift? An airfoil produces a lift force when fluid flows over it. But what is the source of this lift? Is Bernoulli's principle, or Newton's third law, responsible for it, or both the effects? What's that mean? Don't worry, we are honored to invite the AE brothers to present an experiment to demonstrate how the wings generate lift. Welcome the AE brothers. Check it out. What we need: a pearl plate, simple tape, double-sided tape, card paper, wooden stick, straws, scissors, cutter, pencil, and ruler. Here we go. Use the cardboards and double-sided tape to build the base of the demonstrator. We use pencil to mark 2 points in to give the reference for drilling holes to put the sticks in. For the airfoil part, we cut 2 pieces of card papers with length 15 cm and width 10.5 cm to act as a section of wing. Cut a straw in 2 shorter parts and stick at the bottom part. Keep 1 cm at the trailing edge and seal it with tape. The airfoil model done. Stab holes in the corresponding positions make the airfoil model to pass through the 2. Sticks. 2 more short straws are needed and cut it open like a flower shape, then stick on the base. As we need to keep the airfoil at a certain level and ensure that the airflow can pass through both the top and the bottom part. An extra long straw joins the 2 sticks together. the lift force demonstrator is done. We use a fan for the wind source. And you can see the airfoil start floating up. The lift is generated by the wind passing through the airfoil. This is a simple demo with present of lift force. It's quite incredible how engineer can imagine this, right? Now we are going to unveil the physics behind this demo. This shape here represents the cross-section of an aircraft wing. This view is if you are looking at it from side, for example from the wingtip looking towards the plane. So one of the most common bits in correct theories, which is taught, is something called the equal transit theory, which is based on the Bernoulli principle. So the explanation that this theory gives is that the airflow, the air which is hitting the wing, splits as it hits the front of the wing. The air passes over and under the wing and rejoins at the back of the wing at the same time. So for this to happen, the air flowing over the top of the wing has a further distance to cover over the curved surface. Therefore it should speed up. The speeding up air causes an area of low air pressure above the wing. The air which passes underneath the wing slows down, because it has a shorter distance to travel. And this causes high air pressure below the wing. The end results, this theory states, is that it's pressure difference above and below the wing which causes the wing to move upwards. And this upwards force is more commonly called lift. Now there are a few aspects of this theory which are correct, but it doesn't tell the full story. The equal transit theory is a beautiful way to explain lift, but it's not completely correct. The first mistake pertains to how two particles starting from the same location reach the trailing edge at the same time. The second mistake is that you cannot apply Bernoulli's equation between two streamlines. The better explanation is that lift is generated by a wing or an airfoil, that turning the airflow and redirecting it downwards. It's not a pressure difference which creates lift. The airflow hits the front of the wing and splits the same as before. Also, Bernoulli was correct when it talked about the difference in pressure above and below the wing. And it was also correct in saying that the air which flows over the top of the wing speeds up. Now the air which passes over the wing is kind of sticks to the top of the wing and follows the curve of the upper surface. This sticking phenomenon is known as the Coanda effect. As the airflow leaves the wing at the back, it leaves a slight downward angle because of that curve. That downward deflection also affects the air which passes under the wing and also turns it in a downward direction. It's turning of the airflow which causes lift. More lift can be generated in two ways. The first is by increasing the speed at which the air passes around the wing. This is generally attained by simply flying faster. You can also increase something called the angle of attack. This is the angle of the wing relative to the airflow. So in this example, you can see that the wing is pretty much pointed directly into the airflow. However, if we increase the angle of attack, you can see that the wing is tilted backwards. This creates more lift because the airflow is turned downwards at a sharper angle. Now there is a danger to increasing the angle of attack. If you increase that angle too much, there will come a point where the airflow cannot turn and follow the top of the wing. When this happens, the airflow will separate from the top of the wing. This is what happens when an aircraft stalls. There is no steady flow of air over the wing. Therefore the wing stops producing lift and the plane begins to literally fall out of the sky.